chapters, and he has delivered globally invited talks and seminars and participated in numerous international conferences. Professor Gogate is consultant to many industries in process intensification, process improvement, and wastewater treatment. I don't think so there is any award left, but he has received almost all the awards which is possible at this age. I'll just name a few of them. He is a fellow of International Academy of Engineering, New Delhi, and also IICT UK. He has been involved in many international collaborations with INPT, France, University of Cape Town, South Africa, Hamburg, Germany, University of West Hungary, and in Scotland also. He was also visiting associate professor at Purdue University, USA in 2010. With this brief introduction, sir, I invite you to please enlighten us with your lecture.
Yeah, thank you, Manish, for that nice introduction, and especially updating it to yesterday's citation. So that was quite nice of you. And I also thank Dr. Dasgupta for inviting me and kind of inviting me to present the lecture here. So of course, I'm going to present lecture based on whatever research we do at ICT. And so I'll just share the slides and then we can start. Okay, yeah, just confirm whether the screen is visible and
yes, sir.
Also,
Yes, sir.
Yeah. Okay, fine. So let's begin, and I'm going to talk about process intensification aspects related to different chemical processing applications using cavitational reactors. And this is based on whatever research we have been doing at ICT. Definitely, there is a large research group who is working on different aspects of cavitation. So as I said, I'll be just speaking, and I have tried to make it general because the audience is going to be from diverse field. So I'm trying to make it as general as possible. Of course, giving some examples, but not going into too much of mathematical aspects or equations or making it as a research-oriented presentation. But of course, if you have any queries, we can always have discussion towards the end of the lecture. So definitely, I'll be speaking for about 90 minutes or so, and then we can have a discussion ranging for the remaining part of the lecture. So I just do not want to be just monotonous and covering the entire 2 hours, but we will have some discussion from your side as well. Right. Okay. So let's look into what exactly is cavitational reactor. So cavitational reactor basically is a novel form of multiphase reactor where the energy input is in the form of fluid kinetic energy. We call it as hydrodynamic cavitation, or it is in the form of sound energy, and then the reactor is called as Sonochemical Reactor or ultrasound based reactor. Okay, the main important theme in all these operations is that the introduced energy is collected and delivered in the concentrated form through the cavitation phenomena, and these reactors definitely can be applied for intensification of different chemical as well as physical processing applications. When I say the intensification, the benefits can be in terms of intensified rates. Say, for example, I'm carrying out the reaction, then definitely intensification will be in terms of reduction in the time of reaction, or the intensification can be in terms of higher yield. So definitely the benefits are going to be dependent on the specific application. But yes, there is a lot of promise these cavitational reactors hold. Initial understanding into cavitation definitely was with a focus in terms of how to avoid it in hydraulic devices. So those with chemical engineering background or even mechanical engineering background will realize that cavitation does play a problem whenever you are dealing with hydraulic devices. Suppose you are using a centrifugal pump for pumping liquid from one place to other. Then if I operate it below a certain suction head which is required, then I might go into cavitating regime, and that is to be avoided there, because if you generate cavitation in centrifugal pumps, definitely that can give you erosion problems and your material of construction may not remain stable and there will be a lot of problems, right? So initial understanding definitely was in terms of how to avoid it. The second problem which was felt was in World War days, whenever the large propeller ships, which typically have impellers associated with it, they were moving at a high speed due to very high rotational speeds of the impeller. There also cavitation was occurring, and then you were having problems in terms of, again, the erosion of those impeller blades, and definitely that needs to be avoided. So initial understanding into cavitation was with a focus in terms of avoiding it because of the detrimental effects in the hydraulic devices. Now the hypothesis is that if cavitation is creating problems in terms of erosion of the metals, then definitely there is a large amount of energy which is associated with it, because any erosion from the metal surface will definitely require a lot of energy. Now, if I can use that energy and try to use it in a positive manner, definitely a lot of intensification can be achieved, a lot of benefits can be achieved. Of course, we need to control the energy released so that there is no detrimental effect on the MOC of the reactor, the material of the construction of the reactor, and then I can harness the positive effect. So definitely some engineering inputs will be required so as to only harness the positive effects of the reactors. Right, so this talk is going to give some basic aspects of cavitation. We have already seen the concept of cavitational reactors as a whole. We'll try to focus on different cavitational reactors, what different configurations are available, what could be suitable for industrial operation, what could be suitable for some lab scale analysis. We will also try to have some recommendations in terms of what can be an optimum design and operating strategy. This is, of course, based on a lot of work which was carried out at IICT in terms of theoretical simulations as well as the experimental verification. Then we'll look into different case studies just to see what benefits you can get. And these case studies will be related to the theme of this particular training program related to sustainability. And we can also kind of look for some concluding remarks. Now, before going into the chemical engineering aspects of the lecture, let's try to look into nature. So nature is also utilizing cavitation. So typically this study was done at University of Twente, Netherlands, and they had kind of done a recording of snapping shrimp, which is a marine organism, for actually visualizing what exactly is happening, and it is also equivalent of cavitation. Now, snapping shrimp, if you look at this particular top view, things are going to be clear. So these are the jaws of this particular shrimp. These are going to oscillate, of course, at a high speed. The recording is done in a slow motion. So you can clearly see that something is released here. Yes, this travels a certain distance and then kind of disappears, right? So this is essentially things are happening whenever this snapping shrimp encounters any prey around it or any food around it. So it tries to oscillate the jaws, throws a cavity, it is equivalent of a cavity, which travels a certain distance and then collapses. Now, if you do some fundamental analysis and try to measure the pressure at different levels, so point number 1 is equivalent of jaw oscillation. Point number 2 is where the cavity is going to be just thrown. And this point number 3 is at the collapse of the cavity. Clearly, there is a large pressure pulse which is going to be generated. Now, don't worry too much about the sound pressure values. These are enough to paralyze a prey, may not be enough to actually do some chemical reactions or anything. But yes, there is a large pulse, pressure pulse, which is generated, which means that whenever cavity collapses, certain energy is going to be released and that is converted into a pressure pulse. Now, this fundamental study was published in Science. So definitely there is a lot of credence which is associated with this particular study. Now, what do I want to do? I'm not going to be satisfied just with just one snapping shrimp, but I want to replicate nature and at multiple locations in the reactor, right? I want to have multiple such snapping shrimps working in my reactor, generating cavitation and releasing the energy, which can be then used for transformation, right? So we have already seen that, yes, it has a lot of potential. It was causing problems like the cavitation erosion in propeller blades. You need to use it properly. And that's where the engineer's job is going to be extremely important. You need to design the reactor properly so that the positive effects are going to be harnessed for all the changes which are required for the specific application. At the same time, very important, there should not be any problems with the reactor operation. Okay, there will not be any erosion of the surface, because if there is erosion, then definitely the stability of reactor will be a question mark, and then you need to look at the problems associated with the reactor operation. So I do not want any negative effects, but I do want positive effects which are going to be focused in the liquid, and then I can get different benefits from the cavitational reactors. Right. So let's now look into what exactly is cavitation. Now, cavitation typically starts with a nuclei, and depending on what pressure field is introduced into the system, that generated nuclei is going to go an expansion phase. It will reach a certain maximum radius and then undergo a rapid collapse phase, which will be often adiabatic, and then the cavity will be completely collapsed. So what is happening here? The growth phase is gradual. The collapse phase is very short. A very simple example which many of us have experienced is inflating of a rubber balloon, right? So whenever we are trying to inflate the rubber balloon, you are going to putting in the energy into the system. The balloon is going to grow, and then it will reach a maximum critical radius depending on the strength of that particular material, and then just collapse, and you will hear a loud sound. So same thing is happening here. It's going to reach its thermodynamically stable maximum radius, then undergo a rapid collapse phase, and whatever energy was accumulated, that will be released in the form of, say, high temperature pulse or high pressure pulse. If there are chemicals present there, then you can also undergo pyrolytic type reactions, and different effects are going to be seen, right? So let's look into now what key effects are expected. Yes, you will have localized intense pressure and temperature conditions. You will have concentrated energy at the location of transformation, because this is going to happen at a microscopic level. So the energy will be released right at the location of transformation. You will always have high intensity turbulence, which is going to be generated in the system, which will give you increased transport coefficient. And suppose there are some chemicals like water is present in the system, it will undergo thermolytic fission or dissociation reaction and will generate highly reactive free radicals. And if you combine all these effects in positive manner in your process intensification, you are likely to get an order of magnitude reduction in energy requirement for any physical or chemical transformation. So definitely there can be reduction in the energy. As I said, there can be different intensification benefits depending on what is the specific application which you are going to use cavitation for. So let's look into some classification of these effects as well. Now, if I want to look only at physical transformations, then I need to focus on the high intensity turbulence, the increased transport coefficient, because it's a physical process. It's dictated by mass transfer. It's dictated by the fluid flow. So only turbulence is going to be useful. That's going to give an increase in the transport coefficient, and the energy dissipation, of course, will be required. That will give me the benefits in terms of higher rates of processing. But if it's a chemical transformation, say a hardcore chemical reaction, or it's a wastewater treatment type application where you need to oxidize chemicals which are going to be present, then I need to also maximize the chemical effects of cavitation, which will be in terms of local hotspots. It can be in terms of highly reactive free radicals which will be generated, and then I need to get the desired intensification in the chemistry part of that. So depending on the application, there might be a requirement that I can definitely maximize the chemical effects, or I can maximize the physical effects as well. Now I could just see a comment whether there is any problem in terms of the voice from my end. I think it is clear, or it's a little bit of low voice.
Your voice is very clear, sir. No
Okay. So I think then the problem is at the participant end. So I just wanted to confirm that. Okay.
Yeah.
Right.
Yeah.
So the key effects can be classified into physical effects or chemical effects, and then definitely I can maximize the physical effects or chemical effects depending on the operating conditions which I can use. Okay. Now the operating conditions, say in terms of ultrasonic reactor or the sonochemical reactor based on using ultrasound. So there the operating conditions will be in terms of the frequency of irradiation and the power dissipation which is going to be used. And the same ultrasound typically can also be used in diagnostic or medical. Okay. So diagnostic, definitely I do not want cavitation to happen, because whenever I'm using diagnostic ultrasound, say an application in medical field, sonography, right? It's always used based on using ultrasound. So there definitely I do not want any cavitation to happen, because if cavitation starts happening in my body, definitely that's going to be detrimental. And there, some of you will quickly remember that there are always talks whether too much of sonography is a problem or not, right? Whether it gives some changes in the body. But if you control the operating frequency, typically very high megahertz range, and control the power dissipation, typically lower power dissipation, then definitely you will not have any side effects of ultrasound, and the diagnostic ultrasound will work. But remember that the same ultrasound, even in medical application, will also be used for destructing tumors, right? And there is an upcoming field which is coming up in terms of high frequency focused ultrasound, HIFU, which can be also used for treatments, the treatment of tumors. So in medical field also, you are using same ultrasound for diagnostic. You are using same ultrasound even for tumor destruction. So that all that tells you is that depending on the application requirements, you can tailor the intensity of cavitation based on operating conditions. Let's give me one more example, say from chemical engineering. I can use cavitation or ultrasound for crystallization, which is just getting the product in pure form in specific size which I want for the crystals. So crystal characteristics is going to be important. But I can use same ultrasound even to destruct that particular compound if it is present in wastewater. So let's take example of pharmaceutical compound. Say ciprofloxacin, it's an antibiotic, well known. I can use ultrasound to tailor the crystal size distribution of this particular solid compound. There I do not want any chemical changes to happen. But if that same ciprofloxacin is present in ppm level in my wastewater, then definitely I will have to destruct it, because that should not go into natural resources. So in that, definitely ultrasound can be used, and I can destruct that same ciprofloxacin compound of course, using a different set of operating conditions. So depending on the applications, you need to optimize the operating conditions and try to make use of either the physical effects or the chemical effects in terms of generation of free radicals, the local hotspots. So depending on the application, definitely, as I said, we can tailor the application. Okay, right. So these are just the effects, and if I definitely control cavitation, definitely I can do wonders in terms of getting the process intensification benefits, as well as reducing the energy requirement, which is going to be very useful. Because if you suggest anything, so those working in industry and joining this particular module will quickly understand that if they suggest something to management for any change, the management is always going to come back with what are the typical operating costs, what will be the typical payback. So definitely the cost of treatment or the cost of processing is going to be important, and then only that can be justified. Right, so we are going to see into different avenues, and but important point is that you need to reduce the energy requirement for any physical or chemical transformation. Right. Okay, let's look into now how cavitation is going to be generated. Now, in the case of two modes of generating cavitation, one is based on using ultrasound. So typically in ultrasound, this is just a simple representation of an ultrasonic bath. You require a transducer, which is basically a device which is used to pass ultrasound into the system. So when you pass ultrasound, you will have alternate compression and rarefaction cycles. So in the rarefaction cycles, the liquid molecules are going to be pulled apart. And if the molecules are pulled apart to a distance which is more than the critical distance which is required to hold these molecules together, cavities or voids will be generated, and which in the alternate compression rarefaction cycles will grow in size, undergo different stages of cavitation, and then finally collapse, releasing the energy. So this is in terms of the ultrasound use, where there is an ultrasonic pressure field which is used to generate cavitation, and this is called as acoustic cavitation. In the case of hydrodynamic cavitation, you have a pipe flow where you are having a typical orifice. It's basically a constriction. There can be either an orifice, there can be either a venturi or just a throttling wall. Again, the chemical engineers will quickly understand that whenever I have a restriction in the geometry, my local velocity is going to go up, which means that the pressure is going to fall down. And if the pressure falls below the vapor pressure of liquid at that particular temperature, cavities are going to be generated. Downstream, the pressure recovers, and there are a lot of turbulent eddy fluctuations which are going to happen. And these turbulence is going to, and the pressure field variation is going to drive the different stages of cavitation. And again, you are going to get the same effects. So in a sense, you can generate cavitation using ultrasound. You can generate cavitation using alterations in the geometry, or using high-speed rotating machinery. And then this is called as hydrodynamic cavitation. So depending on the two modes of generation, you can either have an acoustic cavitation or a hydrodynamic cavitation. Okay, let's look into now different types of acoustic cavitation reactors which are readily used in lab level. So suppose I want to simply start with the lab scale device, right? So I can use ultrasonic horn, where I'll have a reaction mixture, and I can just immerse my transducers right into this particular reaction mixture. So this is the transducer which is immersed into the reaction mixture, and this is typically useful for a lab level experiment or characterization type experiments, or in systems where a continuous operation is going to be possible. right? Because I can just have a similar arrangement where the material is going to continuously flow in and out of that particular vessel. So then you can use ultrasonic horn type configuration even at large scale for continuous processing. But most of the times, this is going to be used for a lab level experiment, typically characterization experiments. Now in this, what is happening is your ultrasonic horn or the transducer is in direct contact with the reaction mixture because it's directly dipped into this particular reaction mixture. So you might have some limitations based on what material of construction you are using and what is the typical volume or what is the typical type of liquid you are going to process. So for example, if you are thinking of an acidic reaction, chemistry people will again understand that acidic systems will always have some interference with the material of construction.
This attendance is of 31st May.
Okay, can I continue, Dr. Dasgupta?
Yes, sir. Yes, sir.
Yeah. Okay, fine. So depending on the direct contact, there might be some limitations where you have a problem with the MOC. But in indirect contact, your solution, which is there in this particular tank, does not have direct contact with the transducers. So the transducers are attached at the bottom of this particular vessel. And this will be bit safer because there is no direct contact. At the same time, because there is no direct contact, the typical intensity of cavitation, which is likely to be generated, is going to be lower in this case because of indirect irradiation. So on one hand, I have an advantage that there is no direct contact, so there is no problem in terms of the material of construction, but the cavitation intensity is going to be a bit limited because of indirect irradiation. Okay. Of course, my ultrasonic bath can also be used for a scaled up version, and the volume will be dependent on the number and arrangement of transducers. So I can just have a larger holding vessel here. I have number of transducers which are going to be attached at the bottom, and then I can have uniform distribution of cavitational activity. Now, in this case, the formic acid solution is just given as an example because this setup was used for some degradation studies. So in general, it just talks about a reaction mixture, right? So you can take any reaction mixture or any liquid which you are going to process, and that can be taken in this particular vessel, right? So this is just basic difference between a direct irradiation type and an indirect irradiation type. Now, in the case of indirect irradiation, I can also have different possible variations. So I can have a rectangular flow cell now with opposite faces housing multiple frequency, multiple transducers. So these are just the transducers. So on a rectangle, you will have 4 sides. So the 2 sides will be connected to one particular frequency. The second side can be connected to other frequency. Now, the idea here is trying to arrive at an optimum configuration, which will give me uniform distribution throughout the reactor so that my processing becomes uniform. And if I am using multiple reactors, multiple frequencies, then there will be some interference and you will get higher intensity of cavitation. So that's the logic of using a dual frequency reactor. I'm just making the cavitational activity uniform in the reactor. At the same time, I'm going to make it intense. Again, this is going to be dependent on the application. So some applications may not require an intense cavitation, right? So suppose, for example, again, crystallization. Definitely intense cavitation is not required because I just need to tailor the size distribution. I am in no way thinking of degrading that particular compound. Okay, so in that case, definitely lower intensity cavitation will be helpful, right? But if it's a wastewater treatment application, then definitely higher intensity cavitation will be required. Another variation, again, a hexagonal transducers just gives me flexibility in terms of having more number of transducers on the surface so that the processing capacity can be increased. You can also have an annular quartz tube where I can use a combination of ultrasound with UV irradiation, say for a combination of ultrasound plus photocatalytic oxidation, say in the case of wastewater treatment. This is again an idea, right? So I can have a hexagonal flow cell. The transducers are going to be attached to the side of the tank and then sonication can be achieved. So these were just few examples for the ultrasonic type reactor. Let's look into some examples for the hydrodynamic cavitation type. Now, hydrodynamic cavitation typically is applied in recirculation mode. So what do I mean by recirculation mode? I'll have a feed tank. Then I'll have a cavitating zone. So here it is written as first stage homogenization, second stage homogenization. I'll have a pump which is going to recirculate the liquid from the feed tank, pass it through this particular cavitation zone, and then again I'm going to get it back. The flow rate of circulation typically will decide on the intensity which is going to be generated, as well as the number of times the liquid is going to be exposed to that particular cavitation zone. So this is typical loop which can be constructed for a high speed or a high pressure homogenizer. You can also have same loop, but now this is a little bit modified in terms of the type of cavitating device which you are using here. So for example, here you have an orifice plate or you can have a venturi here. The liquid is going to pass here. I can have the wall configuration such that I can control the flow of material into the cavitating device depending on what is the typical intensity which is going to be required. And then it's going to come back here. I can also provide jackets. Suppose I want to control the temperature or I want to heat it to a certain level. So that flexibility can be introduced here. And this particular orifice plate or venturi can also have different geometric configurations. So this is just one example of the different plates that can be used. And depending on the plate geometry, the characteristics can be controlled. So in a sense, this setup provides tremendous flexibility in terms of controlling the intensity of cavitation. Now, why I am stressing this again and again is because depending on the application, you need to control the operating intensity and just harness the beneficial effects, right? I do not want any damage to the reactor. I do not want any damage to the processed liquid, right? There should not be any chemical changes which are going to happen when these are not required. Okay, so that's where you need to have flexibility in terms of controlling the intensity of cavitation, right? There are some more designs which are possible. So this is typically a stator rotor type design. So you have a rotating cylinder and these are provided with holes or indentations. And when the liquid is going to flow through it, it's going to generate a lot of turbulence. And this turbulence is clearly reflected in terms of this particular velocity circulation, which is mentioned here. And this is again operating in a recirculating mode, though this has an inline heat exchanger, whereas the earlier situation, you had the heat exchanger right at the tank itself, right? So again, depending on the application, such configurations can be modified. You can also have a combination of ultrasonic flow cell with hydrodynamic cavitation. So in the same flow loop, I am now introducing ultrasonic flow cell. Now the idea here is that the processed liquid will be subjected to more cavitation, first in the form of orifice plate, and then when I'm going to ultrasonic flow cell, definitely again cavitation will be exposed and I'll get higher effects, right? Now looking at the important design parameters. Now to control the operation, you need to also play with the design parameters. So in the case of ultrasound-based or sonochemical reactors, you have intensity of irradiation, typically the power dissipation per unit area. You have the frequency of irradiation. So typically low frequency reactors like 20 kilohertz frequency, 50 kilohertz frequency are going to be suitable for physical processing, because they generate a lot of physical effects in terms of turbulence. Whereas high frequency in the few hundred range, like 200, 500 kilohertz, are known to generate chemical effects, and then those will be helpful for say wastewater treatment type application, right? Then you also have different properties of liquid, which is going to decide the cavitational intensity. And the important properties are vapor pressure, viscosity, surface tension, and presence of dissolved gases or impurities. Now, if you remember the very first slide, we had nuclei, which is going to be there, and then that's going to give me the cavitation in the application. So this nuclei can be in the form of dissolved gas or any of the solid impurity that is going to be present in the system. And these dissolved gases definitely are going to be there. Suppose if you take a glass of water, definitely there are dissolved gases in that in the form of dissolved oxygen. There can be some impurities also, which are not visible, say micro level, nano level. Impurities are also there, but these are sufficient to introduce nuclei, and then you are going to get the cavitation. Operating temperature again also plays a role. So depending on the required intensity, I can definitely optimize these parameters. Similarly, in the case of hydrodynamic cavitation reactors, typically I can operate with cavitation number, which is the pressure drop per unit kinetic energy. And this should be less than 1. More specifically, people have recommended that this cavitation number should be in the range of 0.2 to 0.4, and there you get maximum effects of cavitation. That doesn't mean that if you are having cavitation number greater than 1, cavitation may not happen, but it only will be in terms of less intensity. And especially if there are gases present, definitely it provides more and more nuclei, and there you can generate cavitation, although with lower intensity. Typically, I can operate with higher inlet pressures into the system, which is going to be generating more intense cavitation. Though definitely I may not operate beyond an optimum value, depending on what system I am using. And because we get conditions of say supercavitation, where not only one cavity is forming, but the entire the pipe can be filled with a lot of cavities, which is going to get a cushioning effect. So I need to avoid the supercavitation. And this typically be established based on either the theoretical simulations, or you can do good experiments and trying to decide, depending on the configuration, what will be the optimum value of pressure. I can also use lower free area. Typically, it means that you will have higher turbulence. Of course, the pumping capacity also is going to be higher. And for orifice, I can always use plates with smaller size holes and large in number. Whereas with venturi, typically I can reduce the geometry in terms of the length of venturi or the throat to pipe diameter ratio and generate more intense cavitation. So all this is definitely going to be useful for the designing of cavitation reactors. So some recommendations have been given. Okay, let's look into some applications, some general applications where cavitation can be used, and then we'll follow it up with some specific case studies as well. So these are the core areas where you have applications of cavitational reactors ranging from chemical synthesis, wastewater treatment, cell disruption, enzymatic reactions, crystallization. A lot of people are nowadays interested in natural products. So there are some examples even in the natural product extraction. What benefits you can get? So in chemical synthesis, you can have reaction time reduction. Then you can increase the yield of reactions. You can have switching of the reaction pathways. Now, this is very important when there are a lot of side reactions which are going to occur. So you need to maximize the selectivity. And if you can tailor your ultrasound so as to switch the reaction pathway to a specific one or the desired one, then definitely selectivity will be much higher. I can also use cavitational reactors and carry out the same application under mild conditions of temperature and pressure, right? So if a conventional reaction is requiring about 80 degrees Celsius for the onset, if I'm using cavitation, it might happen that the same reaction is going to progress at a faster rate, even at 50 degrees Celsius, because of the local hotspots which are going to be generated. So definitely there will be some cost saving because I do not have to heat it to 80 degrees Celsius. So that is another benefit which I can get. Some reactions are also categorized by an induction period. Even your crystallization, which is formation of crystals, typically you will have an induction period. So if you can reduce it, definitely some advantage in terms of fast processing you will get. So ultrasound or cavitational reactors can also be used for reducing the induction time. In the case of heterogeneous systems, you can increase the effectiveness of catalyst. So again, those from chemistry background would quickly understand what do I mean by catalyst deactivation. So suppose I'm using the catalyst and after some time it starts getting deactivated, say due to deposit of some impurities. Now, if I can use ultrasound, the turbulence generated by the cavitation can avoid any kind of deposition of materials. Definitely that will keep my catalyst clean, and there will always be increase in the effectiveness of the catalyst. You can also have initiation of reaction pathways based on highly reactive free radicals, and typically we'll understand that again the reactive radicals are going to react at much higher rate as compared to molecules. So definitely it will mean that you have a faster rate of reaction. So your time cycle will also get reduced. In the wastewater treatment, typically I am thinking of destructing the chemicals. So I'll have oxidation of complex chemicals, and this can be used either as a standalone treatment or definitely as a supplement to conventional techniques such as biological oxidation. Or some industries might be using some chemicals as well. So I can use cavitation, especially the hydrodynamic cavitation part, and try to improve the efficacy. And then there are different examples where different complex chemicals can be treated, starting with different pesticides, your antibiotics, your phenolic compounds, your dyes, as well as inorganic compounds like cyanides or carbon tetrachlorides. All that can be destructed using a cavitation. And if you refer to literature, there are large variety of reviews and case studies which have been reported with different compounds. Cell disruption again is an upcoming field, especially to recover different enzymes from the cell, right? And typically the conventional techniques require a lot of energy. If you can use cavitation, it requires much lesser energy requirement. Of course, the intensity of cavitation needs to be controlled here because I do not want any damage to the enzymes or the recovered products. Because natural products, again, these are going to be susceptible to oxidation. So suppose I am using cavitating conditions, people are always going to look at whether the compound itself is getting destroyed. So definitely those control needs to be exercised. And I can also control the intensity of cavitation to achieve selective release of enzymes, because inside the cell, the enzymes are going to be present at different locations. And then if I want to selectively achieve the release, again, the intensity of cavitation needs to be controlled. I can also have some enzymatic reactions. So a lot of green processing today talks about using enzymes as an alternative to chemical catalyst, because chemical catalyst, you always require some toxic solvents in the processing, and that is going to create a lot of problems of pollution, right? So people say that enzymatic reactions are kind of greener reactions, but then the problem is these are going to be slow reactions. So typically if the chemical catalyst under high temperature and pressure conditions is requiring few hours, enzymatic reactions might require few days. And typically these are limited by mass transfer. That's why these are slow reactions. So if you can use ultrasound or cavitation in combination with enzymatic reactions, definitely you can get higher activity of enzymes, and your mass transfer limitations can also be eliminated based on the turbulence which is going to be generated. of course, again, I need proper optimization of ultrasound parameters because I do not want any damage to the enzymes, right? And there will be many applications which people have reported in fermentation. Okay, just as an example, I wanted to give. In addition, there are some specific other applications which are also reported, like intensification of solid liquid extraction process. Again, natural product recovery is a good example of extraction which is required. Say active components being extracted from the solid matrix, the plant matrix. You can also have better yields and uniform crystal size distribution in crystallization operation. You can have synthesis of nanocrystalline materials. Very important when we talk about catalyst, because we know that nanomaterials typically give much higher activity. So definitely synthesis of nanocrystalline material is a very useful area. I can also have applications in emulsification where I want to generate a fine emulsion, say oil in water type emulsion. The emulsion generated should be stable, and it strongly depends on what is the drop size which you are using for emulsification. So definitely ultrasound can be used to generate the lower size emulsions which are going to be much stable. And also in atomizations where you are going to generate say spherical particles based on spray drying type application. So there, if you are using ultrasound, definitely you will get lower size. You can avoid agglomeration of the particles, and you can also get uniform size distribution. So those are some of the advantages which you can get in automation. Right. So let's look into now different case studies which are based on the work which was carried out in ICT. And I have kind of going to the theme of sustainable processing, this particular workshop. I have taken the areas, one in bioprocessing, biotechnology type, to convert your sustainable biomass into value-added applications or biofuels, or your waste cooking material, say into biodiesel. So some case studies will be based on that. Crystallization, typically required in pharmaceutical industry, where it is very important that you get the desired crystal size distribution. And then wastewater treatment, because everybody talks about controlling the pollution. If you are coming up with newer and newer drugs, definitely these needs to be also degraded, because yes, whenever I have problem, I'll be happy to take drugs, which is pharmaceutical drugs, of course, and because that is required. But if it enters into your water cycle and you are unnecessarily getting it through your drinking water, definitely that's not a good idea, because I do not want it. Then the side effects are going to be more damaging to me. So treatment is going to be extremely important, and then that wastewater treatment also needs to be equipped with advanced treatment schemes, because most of the conventional schemes are not going to be efficient against new molecules. So some advantages are going to be there. Okay. Now let's look into the sustainable chain of converting your biomass into biofuels or bioethanol. So typically any sustainable biomass, say you have wooden residues, you have sugarcane bagasse. Come November, there is always a problem in Delhi that the burning of wheat straws or the agricultural fields is creating pollution. So all that sustainable biomass can also be converted to some value-added chemicals. Of course, the processing costs typically are higher currently. That's why people prefer burning rather than sending it to industry and trying to process it into some value addition. But if you have that sustainable biomass, you can pre-treat it to remove lignin. Then there will be the hydrolysis of that particular treated biomass, which will give you sugar production. And if you ferment that particular sugar, you can get bioethanol. The same sugar can also be subjected to different reactions like dehydration, hydrogenation, oxidation, and you will get different value-added products as well, like levulinic acid, furfural, FDCA, HMF, a lot of these hydroxymethyl furfural. So a lot of value-added products can also be obtained from that. So this is just a starting material. So here we are going to just focus on the bioethanol production. So suppose I'm wanting to have a pre-treatment of the biomass. So typically it's alkaline pre-treatment. So you'll have any sustainable biomass being taken in a simple agitated vessel where you're going to add the alkali in it and then do the analysis. And in the case of ultrasound-assisted treatment, all you have to do is just insert this particular horn in the same liquid. Of course, you will require mixing because you are processing a lot of solids, but ultrasound can be immersed. And if you compare the extent of delignification, you can very well say that you get a lot of intensification based on ultrasound-assisted operation. And if you characterize it based on high resolution ESEM or TM, definitely you can see a large opening of the structure, which gives you easy access to the alkali, and then your treatment is going to be faster. So definitely you can get the advantage in terms of higher degree of delignification, in lower reaction time, in utilizing lower amount of alkali as well. Right? So because whatever chemicals you are going to use, if you can reduce the consumption, definitely that is advantageous. Now you process that delignified sustainable biomass. So this case study was based on West newspaper, and try to do enzymatic hydrolysis. You are going to get reducing sugar, and if you optimize it, again, you will say that ultrasound assisted is giving you benefits in terms of lower enzyme requirement. There is a significant intensification in terms of the reaction time which is required, and also you are reducing sugar concentration is enhanced. So this is another example of benefits of ultrasound. And the third step which we had seen to generate bioethanol was fermentation. So again, if I'm using ultrasound here in fermentation, the benefits are seen. Okay. So in the case of fermentation, you are again seeing the bioethanol production, and this is reflected in terms of the kinetic parameters. So this is the control kinetic parameters related to mass production and the glucose consumption. And under ultrasound, definitely you are going to get a higher ethanol concentration when you are dealing with ultrasound. So this is the ultrasound based processing, and you are also getting higher glucose consumption when you are using ultrasound. So definitely glucose will be converted to ethanol, and this process is intensified when you are using ultrasound. So for the biomass route to bioethanol, we have seen that if you are using ultrasound at different stages of processing, like the pre-treatment, like the enzymatic hydrolysis and the fermentation, at each stage, you are going to get a certain degree of intensification. If you again try to go into fundamental level, what exactly is happening, then you can do a ESEM images for the ultrasound treated cells, and you can see that the structures are getting opened up without any damage, of course, to the cells which are being used in the fermentation. So definitely there is some opening of structure, which will mean easy access without any damage. And that's the main reason for your expected intensification, right? So this is just the concluding part for this particular thing, just to summarize what level of intensification you are getting. So West newspaper definitely can be used as a sustainable carbon source for bioethanol production. You are getting enhanced productivity due to the use of ultrasound, and the ESEM analysis kind of confirm the favorable effects of ultrasound. Yeah. So let's look into now different lignocellulosic biomasses, because what is going to happen, you may not have a continuous source of one particular sustainable biomass. So you need to develop a system which can be useful for different types of biomasses that can be used. And that's why we did some experiments with different types of biomass, and these are all sustainable waste materials. So peanut shells, right? Once you get shells, once you get the peanuts out, then the shells are usually discarded. Coconut coir, right? Pistachio shells. So all these materials typically have a high content of cellulose as well as hemicellulose, which can be converted to sugars. Of course, the lignin content needs to be removed because that gives the hard structure, the hardness to the structure. But when I am processing it, this lignin typically acts as a detrimental in giving a free access to hemicellulose or cellulose. So essentially, the first step looks at removal of lignin, or we call it as delignification. So alkaline delignification was again tried, and you could get the extent of delignification, which is in the range of about 40 to 45%. When you are and it's dependent on the material which is there. So stability of the material also plays a major role. But yes, ultrasound assisted is giving you intensification. And if you do some XRD analysis, just again to understand the fundamental effects, you can clearly conclude that, that it becomes more crystalline due to the removal of lignin. So that's where the advantage is going to be there in the future processing. Similarly, you can do a ESEM analysis and confirm it, the opening of the structures. So the comparison of the benefits now are presented here in terms of the conventional and ultrasound assisted approach for all the shells. So essentially you are getting higher level of delignification, and the intensification is about 1.7 to about 2 times. So definitely it depends on the type of biomass which is used for processing. Let's look into some biodiesel applications as well. Now, biodiesel, a lot of people have shown interest in the biodiesel production. Of course, it depends on what are the current level of fossil fuel prices. Your conventional petroleum or the fuel which is used, if the prices are large, then people start working into the biodiesel areas. The moment it falls much below, say the $30-40 per barrel, interest into renewable energy kind of dwindles down. But in this case, being academics, definitely we need to look into the biodiesel production level of intensification. And the case study which was based was on enzymatic interesterification assisted by ultrasound. So interesterification is typically a reaction of triglyceride with methyl acetate. You get fatty acid methyl esters, which is nothing but biodiesel, and you get triacetine, which is more value-added product. Now, the difference with respect to the more commonly used transesterification or esterification is I'm replacing methanol with methyl acetate, and instead of glycerol as the product, I'm getting triacetine as the byproduct or the side product in this particular reaction. Now, triacetine has much larger value addition as compared to glycerol. So it can be used as a blend with the fuel. It can be used for other applications as well. So that's why interesterification is more preferred sometimes. But of course, again, it's a slow reaction. And whenever you are carrying it out in the presence of enzyme, again, it's going to be much slower. So typically, waste cooking oil, which is a common sustainable feedstock which is available for biodiesel, was used in this particular study. And the fatty acid methyl esters, typically you can quantify based on HPLC just to confirm what esters are getting formed in the system. So the peaks can be used to identify the type of esters. You can do a typical optimization exercise. So any reaction typically will have the important operating conditions which can be optimized so as to arrive at the best conditions and try to maximize your intensification. So I can study the effect of molar ratio, I can study the effect of enzyme loading. Then ultrasonic parameters can also be studied. So ultrasonic power can be varied. Your duty cycle can be varied. You're again in the presence of ultrasound, you can do the effect on molar ratio as well as enzyme loading. And more importantly, any catalyst, you need to check into the reusability of the enzyme. Now, in this case, you can see that depending on the number of cycles which you are going to use, there is some decrease in the relative enzyme activity, right? So, which means that the enzyme is getting kind of deactivated when you are using. So, one of the governing reasons is definitely you are using enzyme in the chemical processing. So there will be some binding of the chemicals which are used. So active sites will not be available. And of course, there can be some negative effects. Whatever control I keep it on ultrasound, there can be some damaging effects. So which can be again quantified based on the CD spectra analysis. And that was used, and there were indeed some changes which are happening in the structure depending on the helix content or the different turns or the random coils. So yes, there is some change. So I need to again maybe relook at the use of ultrasound or relook at the use of the enzymes itself, maybe use a more stable enzyme. So this ESEM also kind of confirm some changes which are happening in the used in lipase. Definitely intensification was proved, though the reusability was not very successful. In the conventional approach, typically I require excess of reactant. So 1:12 was the excess which is used in conventional approach. You could reduce it to 1:9 when ultrasound-assisted approach was used. Now, what it means if I'm using a lower excess of any of the reactant, now that excess which I'm using definitely will not be consumed in the reaction. So I need to separate it out. So my separation loads are going to be higher when I'm using a higher ratio, right? So 1:12, definitely I'll have a large separation load. When it get reduced to 1:9, then the separation load is going to be lower. So that definitely that's an advantage of ultrasound-assisted approach. You are also requiring lower enzyme. So definitely my operating cost will be lower. The reaction time is significantly reduced. Say from 24 hours, it has got reduced to only about 3 hours. So definitely there is a lot of intensification which is happening. And the biodiesel yield, there is a marginal increase from 90% to 96%. So definitely some advantage you are getting in the yields as well. Okay, so this is just summary, because anywhere again, the executive summary is very important. So any experiment you do, detailed experiments, vary the different parameters. While reporting, such comparative tables are going to be very useful, because this clearly tells what advantage you are getting based on the use of ultrasound. Right? It's just 1 minute kind of explanation. Of course, this was based on 6 months of rigorous experimentation in terms of optimizing all the parameters, understanding, performing different experiments. But just a 1 minute snapshot is going to be extremely useful. Right. Now, after looking into the different reactions related to sustainability, let's look into some applications in crystallization. So typically, sonocrystallization is the application of high intensity, typically 50 to 200 watts per liter power dissipation, low frequency ultrasound to promote and control crystallization. So that's the basic definition of sonocrystallization. And the main effect of ultrasound is to promote nucleation via transient cavitation. So in crystallization, again, the nuclei formation is going to be very important. So if I am using ultrasound to promote the nucleation, definitely the crystallization is going to be faster. And it can also give me the lower sizes of crystals. Again, very important criteria for pharmaceutical processing, because there cannot be any compromise on the final size of crystals which you are going to get, because the drug activity, the bioavailability is going to depend on the size. So there cannot be any compromise. So definitely you need to control the size. So a lot of times reprocessing is required. So in the batch, if you are getting agglomerates, you need to reprocess that particular batch again, which can be avoided when you are using ultrasound, because then you can control the size distribution. Right. There are different problem areas. Agglomeration, we have just seen. Size distribution, again, is a problem. Accretion is another problem, which can give you fines. Growth of the crystals, then polymorph is another problem area. So some of these problem areas can definitely be addressed when you are trying to use ultrasound. Now, how I can control the crystal size while the crystallization is going to occur? So there are some general rules. So cavitation definitely promotes nucleation. If I'm using continuous cavitation, I'll keep on generating nuclei which are going to grow to a certain size, and these are going to result in small crystals. If I just use initial cavitation to give some nuclei, then these are going to grow to a larger size. So larger size. If I give a pulse cavitation that keep on operating ultrasound after specific durations, then I'm going to generate nuclei intermittently, and then they are going to grow to a certain sizes. So depending on the application of ultrasound under different conditions for different time intervals, I can tailor the size distribution to a required value. So cavitation provides typically a non-invasive way of improving the crystal properties, and of course gives an advantage in terms of process control. By controlling the nucleation and therefore the crystal size and size distribution, the yield as well as the product characteristics can be improved. Typically crystallization is going to be followed by filtration. So suppose you are not controlling the crystal size distribution and you are generating too many fines or too many agglomerates in the system, then usually there will be problem in the subsequent filtration or downstream processing. So that can be improved when you are using ultrasound. Definitely you can use ultrasound for manufacturing better quality products and improved productivity, as well as sometimes you can go to nano size levels. So if I want to look at any particular system and try to see how I can optimize the methodology or optimize the benefits for this particular technology. This is just as a slide I am explaining for any kind of new people who might want to venture into applications of ultrasound. Now, typically you need to first look into, for any specific system, perform some simple experiments in the presence of ultrasound and use your conventional approaches, right? Because whenever you are thinking of any new method as a replacement or as a supplement, you need to quantify what benefits are going to be expected. So just do some simple comparison of the ultrasound or cavitation assisted approach and the conventional approach. If you are seeing any benefits, then definitely you need to go forward. Now, benefits can be seen in what? So benefits can be seen in terms of the crystal size. For crystallization, you also have the metastable zone width or the induction time and the nucleation point, and these are going to depend on use of ultrasound. These are also going to depend on the different operating parameters can be used. So then if the positive benefit is seen, then I can start looking into detailed optimization of different operating parameters, say the power dissipation levels, say where I'm going to apply ultrasound, for what time duration I'm going to apply ultrasound. So all these parameters can then be optimized, and that will help you in terms of maximizing the benefits. So finally, you should look at establishing the optimized system for maximum benefits. Then you need to look at the possibility of scaling up, because I don't want to be confined to any technology at small level. I need to look at the larger scale operation. I can also start exploring the design information for other products or other applications, right? So this kind of moving horizontally, applied to different applications, and also try to do a kind of a commercial level analysis. So this can be the path followed. Now, some specific examples. Yes, different materials have been tried. They have shown a lot of benefits in terms of the particle size distribution. So if you're using ultrasonic horn, you get a narrow size distribution, and typically it shifts towards left as compared to without ultrasound. So definitely lower size is obtained and narrow size distribution. Mefenamic acid is another pharmaceutical compound. So without agglomeration, there are a lot of agglomerates which are seen, whereas with ultrasound, you also get plate-shaped smaller particles. So definitely the size and shape can be controlled. Effect of ultrasonic power can also be looked at. As I said, different parameters are going to be important in terms of controlling the size distribution. So I'll have ultrasonic power as one of the size distribution. So in the case of ultrasonic power, if you keep on increasing the ultrasonic power, say from 30% amplitude to about 70% amplitude, you can clearly see a shift from right to left. So this is for 30% amplitude, and this is for 70% amplitude. So what it is meaning, it is becoming narrow, and the mean size is also going to be lower. So definitely this mean size is lower as compared to this mean size. So if I'm using more power, definitely the crystal size distribution is going to be shifted. At the same time, I also need to look at whether there are any negative effects which are seen on the crystals, because remember, same ultrasound can also be used for oxidation of the compound. So there should not be any change which is happening chemically. So that's where the you need to worry both about the positive effects which are seen in crystal size distribution. At the same time, there should not be any negative effects on the chemical structure. Now, how should I look for scale-up aspects? In the case of crystallization, I can think of operating with different modules. So I have a cylindrical type reactor where I have different transducers, typically a 37-liter module which is reflected, and I can just number it up. So NX modules can be stacked up to give the desired residence time. So this is one of the way in terms of scale out. Or I can look at the existing reactor itself. So this is typical existing crystallizer. Typically, it can have anywhere between a few meter cube of capacity. So there, I can use ultrasound. So I can generate nuclei and then insert it into the system, either one time or keeping continuously. Or I can have a flow loop which will pass the same solution through the crystallizer and get it back. So this can be looked at. This is kind of adding to your existing setup. So the same setup will be used, and ultrasonic flow cell can be just introduced into the system. Let's look into some applications into wastewater treatment. Okay, so this we have seen related to reactions, we have seen related to the wastewater treatment. Sorry, we have seen related to crystallization, and now we are going to see some examples, some case studies on wastewater treatment. Dyes are one of the most important pollutants because these give a quick visible appearance for the pollution, right? So even if you have some toxic compounds which are colorless, then you may not be able to recognize pollution unless somebody tells you or you do a analysis. But even if it's a food colored dye and you are mixing it, definitely you will think twice before kind of touching that water or even drinking, right? So color is the most visible indication of pollution, and typically rhodamine B, which is a pink color dye, was used for this particular study and trying to compare the different cavitational equipments. So you can see that hydrodynamic cavitation typically of more efficiency in terms of the molecules degraded per unit energy supplied. So that was one example from dyes. And there are many such dyes which have been degraded or oxidized using cavitation. but only one specific case study was mentioned. Distillery wastewater again is a very polluting kind of industry and typically characterized with very high COD levels. So this typical example had a COD of around 60,000, but in reality you can also get CODs of few lakhs as well. So those are very difficult to be managed using the conventional process. And the worrisome part is that it has low biodegradability. So suppose I want to use any of the conventional approaches like biological oxidation, definitely it gives problem because the BOD to COD ratio is quite low, which means it is biocalcitrant or with non-biodegradable type effluent. So then you can think of say cavitation as a pre-treatment technique and try to change your BOD to COD ratio, which then can be easily biodigestible or biodegradable. So different combinations can be tried out. In addition to the cavitation, you can also have ozone as an oxidant. So if you have a combination approach of ozone plus aerobic oxidation plus ozone, we have ultrasound also in the next slide, but here it's just shown as a comparison for the efficacy of ozone. Again, it's an advanced oxidant. So if you have a combination, you typically get 80% degradation as against only aerobic oxidation, which is around 35%. And look at the time as well. So untreated only aerobic oxidation, you required about 60 hours for the digestion. But if you look at the combined approach, so you are getting about 2 times increase in the COD reduction, and you are getting the reduction in the time of treatment, say from 60 hours to about 40 hours. So definitely the processing capacity is going to go up. Ultrasound also can be used in combination with ozone, and then you can get some more benefits, right? So yeah, it's about 11:20 now. So we'll have another 10 minutes and then we'll have interactions. So I just wanted to highlight one particular case study because people do worry about whether the technology, any new technology is available on a large scale basis or not. So this was a project which we did with one of the US based companies, Ecosphere Technologies, and trying to take it from concept to actual commercial reality. This is a hybrid advanced oxidation reactor. So this is typically works on a combined operation of ultrasound-based acoustic cavitation, hydrodynamic cavitation. It also has electrochemistry associated with it, electrochemical oxidation, and ozone. Now, the key advantages which you get when you are trying to combine all these operations is, one, you will require lower dosage of ozone, because ozone typically, if you look at any of the operating cost or the capital costs for ozone generator, these are going to be quite energy intensive or costly proposition in terms of the advanced oxidation processes. So if you can lower the dosage of ozone by use of combination, definitely your treatment costs are going to be lower. It can be also applicable to a wide range of effluent or water streams because you are able to generate different oxidizing species which are going to give you a wide range of oxidation capacity. So definitely applicability will be there. So actual depiction of this particular ozonics reactor. So this is a ozonics reactor which is kind of modular in construction. So what do I mean by modular? It can be simply mounted on a mobile trailer and then taken from one site to other, because typically further the oil and gas wells where the main application of this ozonics reactor was demonstrated, they have a certain lifetime for the well. Okay, and the lifetime can vary depending on the oil capacity, depending on the exploration rate at that particular site, and sometimes you may not intend to do a large capital investment at that particular site, because we know that once the oil well is dried, then that capital investment may not be of any use. So sometimes you require such mobile solutions, and the Ozonics reactor was developed with that particular understanding. The second application of this modular unit can be in lakes. So suppose I want to treat some part of lake which is contaminated based on localized pollution. So typically lakes will have some input from discharge from say industries, or rivers will have some discharge from industries. They will have some discharge from some municipal corporations. So that's a source of pollution, right? So at that source, if I want to treat, then I can use such modular units and for water treatment, and it kind of operates at very high capacity where that can be operated. So this is just a modular kind of representation. Different radical reactions are going to occur, which will give rise to different oxidants. So if you have cavitation, water which is going to be present, which will be dissociated into hydroxyl radicals, which have a much higher oxidation potential. And you can always have some recombination of hydroxyl radicals, which will give you hydrogen peroxide, of course, which is going to be another oxidant. You can also have ozone added up, and then when you combine it with cavitation, you again get hydroxyl radicals. Electrochemistry also are going to give you hydroxyl radicals. So when I'm combining this, essentially I'm going to generate more and more hydroxyl radicals in the system, which means that the oxidation capacity is going to be definitely increased. So when we were looking at the concept of this particular system, we were looking into the little bit of theoretical simulations, trying to optimize the system, trying to arrive at an optimum design. So we looked into some cavitational activity distribution across the pipeline type reactor which is there, tried to quantify the levels of turbulence in the reactor. We also integrated it with different chemical reactions that are going to be possible in the systems, and that helped in terms of predicting the radical formation, and of course arrived at optimum design and operating conditions. So some results quickly we are going to get. So cavitational activity distribution more or less is uniform. Of course, there are some higher zones which are local to the transducers, so that are seen here, but more or less it is uniform. In terms of the velocity distribution, yes, there is kind of distributed all over the reactor. Again, there are some focus zones which are seen at the entry, but that is corresponding to the liquid entry, so that's going to get radical concentration definitely is going to be higher. So that means a lot of hydroxyl radicals are going to be generated in the system, which will give you higher oxidation capacity. The typical success stories were mainly in the oil and gas fields, over 1200 hydraulic fracturing operations at different levels in US mainly. And this showed proven applicability at commercial scale and for different water samples. So definitely it was kind of successful. And the quantitative confirmation was in terms of the bacterial load, acid producing bacteria. So typical recycled effluent had a very high load, which was kind of treated was very less. And the results were also reproducible. So this is just a kind of an inlet EN25, and you could get different passes through the reactor, and definitely it was giving similar levels of treatment. So it was reproducible as well. It was not that just one-off treatment. And you can clearly see an influent and the treated effluent at the actual commercial site. So the untreated effluent was typical black color effluent. When you pass it through the unit, it was kind of a milky, and it had a lot of success in terms of recycle. So definitely it's treated. And one of the parameters which also controlled the recycle into the oil and gas well, the differential pressure was also seen to be favorably increased. for the ozonics treated fluid. So that's the added advantage in terms of the recycle capacity that can be on a larger kind of area. So typically hybrid advanced oxidation reactor, you get a lot of intensification. There is a mobile platform which gives flexibility of treatment at the client side, and there was proven success stories at different installations. So we are now coming to the kind of end of this particular session. Of course, we have seen a lot of examples where cavitation can be successful. We have seen examples from chemical reactions. We have seen examples from crystallization. We have seen examples from wastewater treatment. There are again large application areas. Those interested definitely can connect with me or refer to literature. Many compounds have been also degraded when you look at wastewater treatment. But yes, still there are some design challenges which are associated. And typically this is related to the uncertainty associated with the cavitation phenomena itself. And yes, there is some non-uniform distribution of the cavitational activity. So your design of the reactor, especially when you want to explore it at large scale, the design is going to be extremely important. So you need to have an uniform distribution of activity in the reactor. So one should definitely look at that angle. Development of new materials for vibrating surfaces and focusing the sound energy away from the surface. So material science also is going to play a major role, because I need to get new materials which will be kind of stable in the operation, and also it will focus your ultrasound so as to get higher intensity. Hydrodynamic cavitation is generally observed to produce less intense cavitation, though it has a ease of scale up. And another problem with hydrodynamic cavitation, though largely successful, is related to the solid handling. So if you are having a system where there is a large solid content, the closed network of hydrodynamic cavitation gives some processing problems. So there needs to be some solution based on that. The typical recommended design on that to go into a large scale operation. So multiple frequency, multiple transducer reactors for the ultrasound based, different geometries, different configurations can also be constructed. In the case of hydrodynamic cavitation, you can have orifice plate, and you can choose orifice plate of different dimensions. So then you will have a lot of flexibility in terms of controlling the intensity of cavitation. You typically need designs which are going to be functional on continuous operations. You can also have combined processing based on the similarity of controlling mechanism. Now we discussed shortly two such combination. One, if you remember, was a combination of ultrasound plus photocatalytic oxidation when we are talking about the hexagonal reactor flow cell. So that advantage definitely is there. And the second combined processing was when we saw about the ozonics reactor, where you had the combination of hydrodynamic cavitation, ultrasound, and ozone, all giving you different oxidants in the system, and then the oxidation capacity will be increased. So these are the typical recommendations which you can take for large scale operation. Right, just to conclude, yes, cavitation is a novel technology for process intensification or process improvement. Dynamic cavitation typically has the twin advantage of greater energy efficiency and higher cavitational effects as compared to acoustic cavitation, because whenever we have like two different modes of cavitation, people will definitely want to check which one is better. So just as a recommendation, hydrodynamic cavitation offers some advantages definitely as compared to the acoustic cavitation or the ultrasound based cavitation. There are many proven examples. We have seen some, only a few in this particular lecture, but yes, there are many more, and if you see literature, you will clearly find range of applications and success stories at lab scale. A lot of academic work is being carried out for different applications. In India also, there are large number of groups which are working on different dimensions of ultrasound. In Europe, in US as well, there are a lot of groups which are working. There are indeed some industrial applications which are successful. There are companies offering technologies, wastewater treatment. We have just seen some companies in US. Crystallization, there are some companies in UK which offer technologies for pharmaceutical industry. Then extraction of natural products. There are some companies in Europe, especially Germany, who offer technology. Then another industrial application which is kind of demonstrated again in Germany is for the intensification of municipal sludge to biogas production. So there you can use ultrasound and try to intensify the biogas production which you are going to get. And definitely I can say that yes, combined efforts of scientists are typically required to harness this cavitation as a technology. So yes, there is still some scope in terms of exploring different applications. In India, the industrial applications are not that successful at this stage. But yes, we can definitely move forward and try to get those applications demonstrated even at commercial level. So just a few acknowledgement to the funding agencies. Definitely, DST, Department of Science and Technology, has been sponsoring projects on wastewater treatment as well as on recovery of valuable products from waste. So that is acknowledged. The UGC also supports the PhD students. Used to support earlier. Now they have stopped those particular schemes. But yes, some of the work was attributed to that. Also to IREL and all of these students over different years who have contributed to some of the work which was presented there. So thank you very much for listening to this particular presentation, and I'll be very happy to answer any questions which the audience may have, or some of the questions might also be there in the chat box, which typically is followed for the webinar type mode. So I'll leave it to the moderators now, and we can have a question answer session.
So there are many questions in the chat box.
Yeah. So should I go to the chat box? Yeah, I can go.
Yes, sir.
And I'll just go and see one by one.
Attendees
Right.
can unmute themselves.
Okay, some of the questions I'll first go through the chat box and try to answer. So automation, I think there was one question on automation. So when I talk about automation, what I mean is the process to generate droplets from a processed liquid, and those droplets can get solidified to the particles, right? So it's kind of a spray drying where you have a solution and then you pass it on to generate a spray which can be solidified to get solid particles. So this is one application of automation. Or you can generate droplets so as to fit the requirement. So that is the process of automation, converting your liquid into droplets, which can be then dried to get a particular morphology of solid materials. So there, typically what happens again is if you're using the conventional pressure-based automation, you may not get the desired droplet size, or you can have agglomerates in the system, or you may not be able to control the velocity at which the droplet comes out of the surface, and then you will have some problems on that. So there, if you're using ultrasound, you will get benefits in terms of control over the velocity, control over the size which you are getting, and then the benefits are going to be there. So that was the kind of example from ultrasound-assisted atomization. That formic acid solution I have already answered. Now, equipment supplier for ultrasonic devices, equipments. Now there are some local suppliers. You can search on Google as well. I don't have ready numbers of them, but I can definitely tell the suppliers. So Dakshin is one supplier which is based in Mumbai, who can typically supply small scale or laboratory scale equipments of say ultrasonic horn or ultrasonic bath. So depending on the requirement, you can give them the requirement in terms of what volume needs to be processed, what is the typical temperature that needs to be arrived, and get an idea about which equipment will be suitable. So Dakshin, you can note down, gives equipments for ultrasonic horn as well as ultrasonic bath. Then there are few suppliers in India who have kind of tied up with European or US suppliers, and then they supply the equipments on their behalf. Of course, these are going to be costlier because of the royalty or the name associated with the foreign supplier. But Group Telsonic is one such supplier who have also supplied sonotrodes or ultrasonic horns or the tube sonicators, which are suitable for processing at larger level. And the application which they kind of specialize, Group Telsonic, is for extraction. So I was talking about extracting natural products from the plant matrix. So such suppliers will be useful. Then there is one more dealer in New Delhi, I forgot the name, but they have a tie-up with Hilscher, which is a German company, which again supplies sonotrodes or ultrasonic horns. So that can be looked at. So these are some of the examples of the equipment suppliers. Okay, I think that's it. Otherwise, not there. There were some comments in terms of good morning and everything. Right. So I think that's all from the chat box. If the audience has any specific doubts, I think the moderator has unmuted you, so you can ask. I'll be happy to answer some questions.
Very good morning, dear sir.
Yeah. Good morning.
Sir, thank you very much for the outstanding lecture, and it has provided a lot of insights. Thanks a lot. I have a question. You had mentioned the application of ultrasound as the cavitation as one of the case study, that is the removal of dye like rhodamine B in wastewater.
Okay.
And is it possible to use this ultrasound and cavitation approach to remove the microbial load that is present in the wastewater, especially the coliform count? As nowadays the most potential problem in wastewater is antimicrobial resistance are drastically enhancing. So can we use this method of ultrasound and cavitation to treat wastewater to reduce the bacterial count and coliform count? What is your suggestion, sir?
Yes, definitely you can use, because see, any microbial destruction is typically controlled by two mechanisms. One is based on the shear which is going to be generated, which is going to just kill the microorganisms or destruct the cells. And second, in terms of radicals, the chemical mechanism. So both are going to be generated, especially in the case of hydrodynamic cavitation. You have large shear which is going to be generated. And yes, coliforms or other bacteria which are going to be present in water, definitely those can be treated. And there are large, again, literature which is available. So yes, hydrodynamic cavitation can be used to treat and reduce the microbial load. There are some interesting applications which are also reported. So I'll just highlight a couple of them. One, definitely you can use hydrodynamic cavitation in your bore wells. So whenever you are kind of using hand pumps to remove water, so there also there is a possibility that some contamination is there in terms of the microbial load. So that can also be treated using hydrodynamic cavitation. So in the flow loop, if you insert a very small orifice or a venturi, at the time of water being taken out from the hand pump, it can automatically disinfect as well. So that one such technology is available. Second example is typically when you are talking about swimming pools. There also the microbial contamination is a major problem, and people use chlorine very often, but chlorine again, there are talks that it's going to be dangerous to the swimmers, and it will also give smell. So there also the people have used again in European countries, because anyway the water is going to be recirculated. So when you are using in the recirculation loop, hydrodynamic cavitation, you can treat, disinfect that particular microorganisms which are present, and then the treated water can be recycled back. Right. So there are many such applications which are demonstrated, and definitely cavitation can be used for killing the microorganisms as well.
Thank you, sir. Thank you very much.
Yeah.
Any other
Yeah.
question?
Any other question?
Any other question by the participants?
I think thank you for the acknowledgement. I could see many chat messages kind of confirming that it was indeed a useful session. I tried to make it simple, not presenting any of the complex mathematical equations. But remember, yes, there is a lot of complex mathematics which also goes into especially the design aspect of that, where you need to solve many equations and try to predict the optimum conditions. But yes, it's good to see that people enjoyed the lecture. So thank you very much.
Thank you, sir.
Thank you, Professor Gogate. Am I audible, Darpan?
Yes, ma'am. Yes, ma'am.
Okay. Okay, Dr. Manish, can you sum up the session and we can...
Yes, ma'am. I'm audible?
Yes.
Yes.
Okay. So I thank Professor Gogate for such a wonderful lecture. So just to sum up whatever he has said in 1.5 hours. So he first mentioned that cavitation is a problem in hydraulics forms, but how to convert that problem into an opportunity. So he first covered the basic aspects, that what exactly is the cavitation, what are the key effects in the cavitating zone, followed by how to classify them into physical and chemical effects, and how to maximize them as per our need. Then sir covered the basic details of the acoustic cavitation reactor and the hydrodynamic cavitation reactor, and he covered a broad spectrum about the various application of such cavitation reactors in chemical synthesis, wastewater treatment, cell disruptions, enzymatic reactions, natural product extraction, and other number of examples. So he has presented various case studies related to biodiesel production, intensification and crystallization, and wastewater treatment related to dye degradation. Well, the overall motto is how to convert that concept into a reality. So he also presented a case study where a company named Ecosphere Technologies from US was involved in the scale up of hybrid advanced oxidation reactor, which involved the acoustic cavitation, hydrodynamic cavitation, electrochemistry, and ozone. So how the various advantages of such technologies was demonstrated, and the modular reactor, that is ozonics. So this can also be used for treatment of water bodies such as lakes. And also he mentioned that the theoretical understanding at the end, that simulations, maybe computational fluid dynamics or some mathematical modeling, are of utmost importance in order to have a reliable scale up for such reactors. So thank you, sir. Thank you, sir, for such a wonderful lecture.
Yeah, thank you, Dr.
Thank you, Manish.
Yeah.
Thank you, Manish, and thank you, Professor Gogate. Sir, you can log out. Thank you for your presentation. Sir, you can log out now.
Yeah, thank you, Dr. Asgupta.